All right, question 8 is up next. We'll do 8, 11, 12, 14, and 16. So question 8, an electron in what orbital in an atom of palladium experiences the least effective nuclear charge? All right, so palladium is right here. So our electron configuration for palladium would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6 takes us to krypton, 5s2, and then 4d, 1, 2, 3, 4, 5, 6, 7, 8 takes us to palladium. Right. So an electron in what orbital would experience the least effective nuclear charge? Right. We are looking for something out here, right? We're looking for some orbital out here that would experience the least effective nuclear charge. Um, so our choices are 3p, which is, let me just change the ink color here. 3p kind of in the middle, right? We're looking for something further on the outside. So let's see, what else do we have? I've got 5s, got 4s. Let me just write these down. 5s, 4s, 3d, and 5p. So other choices are 5s, which that looks pretty good. 4s, nope, we're moving in the wrong direction. 3d, that's between those two. And 5p. Well, 5p is kind of a it's certainly out there, right? 5p would be way out here, but for palladium, right, we don't have any electrons assigned to the 5p orbital. So there aren't any electrons there at all because we haven't gotten to 5p, right? 5p would be right through here in the periodic table. So that would leave us with 5s being the orbital that's occupied and further and furthest from the nucleus. 5p isn't a valid choice because there aren't any electrons there. All right. So that's the answer to that question. So it has to do because of the configuration, right? Correct. Yeah, sure. If 4D was an answer, right? If 4D was a choice, that could work for this. Um, got one request for question 7. Right? I think we can still use this periodic table. So, which two elements have the same ground state electron configuration, right? And to answer that, right, which this is basically saying like which two elements have the exact same number of electrons? Which two elements have the exact same number of electrons? Anyone want to take a stab at this one? Yeah, right. None, right? No two electrons or no two elements can have the exact same electron configuration. Um, so it should be choice E, right? Because each element has a different atomic number. That tells us our number of protons. That also tells us our number of electrons. So um, protons always need to equal our electrons for a neutral atom. So no two neutral atoms, right? No two elements can have this exact same electron configuration. Ions can, but the question wasn't asking about ions, right? So, yeah, choice E, kind of a trick question there. Um, all right, question 11 is up next. Oh, okay, yeah, yeah. Don't worry too much about the quantum numbers. I only went through them in one class. So question 11, question 12, don't worry too much about these. Um, because I went through them in one class. The rest of the classes, I just kind of jumped into the periodic table and showed you that all the same information that we can get from quantum numbers is within the periodic table. And I don't feel like anyone missed anything or lost anything by not going through the quantum numbers. So n equals 3, that would be basically saying I've got three, we can have 3s, we can have 3p, we can have 3d. Those are all possibilities. That's the three here, right? That's our quantum number. L tells us what orbital we are working with. L can be 0, L can be 1, L can be 2, L can be 3. When L is 0, we have our s orbital. When L is 1, we have our p orbital. When L is 2, we have our d orbital. When L is 3, we have f orbitals. So, all right, n equals 3, L equals 2. That's basically saying, okay, we're working with the 3D orbitals. We know we always are going to have 5D orbitals, right? So 5D orbitals times 2 electrons each, right? 10 total electrons possible. I can still ask similar questions like this without having to ask, N is this, L is this. So if you know them, great, right? If you don't know it, don't worry too much about it right now. Question 12 is very similar. Um, so I just defined what L tells us and what N tells us and what L tells us. Um, okay. Well, nine, like we can still answer nine, right? A question like nine, because we know within the third quantum level, right, we have 3s, um, 3p, and 3d. One orbital there, three orbitals there, five orbitals there. So question nine is certainly fair game. Question 10 is certainly fair game because we did talk about the quantum numbers and we know where those fall on the periodic table. Um, question 11 and 12, where I bring in L or ML, that's where I wouldn't bring in those variables. But we certainly should know, right, at n equals 1, we have an s orbital. At n equals 2, we have s and p orbitals. N equals 3, we've got s, p, d. N equals 4 and beyond, s, p, uh, d, and f orbitals, right? We should know that for sure. Um, Yeah, so Abigail, like I think like question 9, right? Question 9 would be something similar to what you'd see on the exam than question 11, um, for sure. Yeah, and so the same, so gain, right, the same kind of answer I would tell you. Like we should know at each quantum level, what orbitals do I have access to? How many of those orbitals, right? So I've got three p orbitals, two electrons each, so six electrons there. Five d orbitals, two electrons each, so 10 electrons there. Seven f orbitals, um, seven times two, 14 electrons there. And then knowing, how many electrons total. Um, all right. ML tells us basically how many different arrangements, how many different orientations. And so ML is negative L to positive L. So in this case, right, this is what tells us we have 5d orbitals. So when L equals 2, that's our d orbital. If I can write. No, still can't write. There we go. Um, And so ML can be -2, -1, 0, 1, and 2. That gives us five different combinations, which is this is where, this is what tells us we have 5D orbitals. So this is not a possibility, right? I can't have a -3 for that. That would tell us we have 7D orbitals. We don't have 7D orbitals. So this cannot exist. The rest of these combinations are fine. All right, for question 12. All right, question 14 and 16. All right, which of the following electron configurations are appropriate for common ions formed by alkali metals when they react, right? So group 1 metals, those are our alkali metals. And when they react, right, when our group 1 metals react, well, I can't cover up the noble gases, but so for example, right, like sodium, sodium is 1s2, 2s2, 2p6, 3s1. When sodium reacts, it loses this electron. And what do we have left, right? We have that noble gas configuration. So we are looking for, oh, there we go. We are looking for anything that's got noble gas configuration. So this, right, this could be the configuration of a group 1 metal after it reacts, right? That actually happens to be sodium plus 1. This also, right, this is the configuration of argon, which that would be equivalent to potassium plus 1. Potassium loses that electron, right, ends up with a full outer shell. This is not a group 1 metal after it reacts because group 1 metals, right, are right here. They've got one valence electron, and when they react, they're going to lose that valence electron. All right, same thing here. We don't have a full outer shell. This is actually a halogen. And then here, same thing. That would be a group 2, right? That would be beryllium there. So just choice A and B for question 14. We're looking for something that's got a full outer shell. It's got that noble gas configuration. All right, I think we can answer the next question. Oh, I wish those would stay put. No, not going to stay put. All right. All right, my fault. All right, we can still answer question 15 here. I was hoping to move it around a little bit, right? What element has the electron configuration of argon 4s2? All right, let's find out where we are in the periodic table. Yeah, question E is not a viable answer because, right, that's not a noble gas configuration. Our group 1 metals, they react to lose an electron and form a +1 cation. Lithium doesn't react to gain an electron, and that's what it would need to do, right, to obtain that configuration. So choice E isn't a possible answer, right? That's not a noble gas configuration. And yeah, just in the future, just ask public questions so everybody can see. All right, we're looking for argon 4s2. So here's 4s2, 3d5, 1, 2, 3, 4, 5. Right, we're looking for manganese. That's where we would be with that electron configuration, right? Argon. So we've got argon, 4s2 takes me to calcium, 3d, 1, 2, 3, 4, 5 takes me to manganese for question 15. Oh, and it was question 16 I should have been doing. All right, question 16. Which of the following symbols are isoelectronic with neon? So I'll go to the next page. I've got nitride. All right, so we're looking for what is isoelectronic, has the same electron configuration as neon. Um, do. All right, we've got nitrogen 3 minus, which is nitride. It's my first time using this program, right? Messing around so many times here. So nitride, nitrogen 3 minus. So we gain 1, 2, 3 electrons. That would take us to neon. Sulfide 2 minus, chloride 1 minus. Those take us to argon. So that couldn't be it. That couldn't be it. Fluoride minus 1, right? We gain an electron. That would take us to neon. So fluoride minus 1, nitride, and then magnesium 2 plus. I lose this electron. I lose one more electron, and that would also take me to magnesium. So, yeah, nitride, magnesium 2 plus, and fluoride would all have the same electron configuration. They would be isoelectronic with neon, right? Nitride, nitrogen is 1s2, 2s2, 2p3. When it gains three more electrons, all right, it's going to end up 1s2, 2s2, 2p6. Fluoride, 1s2, 2s2, 2p5. It gains one electron and it ends up 1s2, 2s2, 2p6 as well. Magnesium loses two electrons, so magnesium 1s2, 2s2, 2p6, 3s2, right? Magnesium 2 plus, it loses these two electrons and we're left with 1s2, 2s2, 2p6. So yeah, those three for question 16. All right, I'll stop that recording.